Hello again. This is Matt 1120 coming to you from the College of DuPage, and this is the second continuation of the lecture entitled Waves and Such. And as always, I encourage you to be active learners as you watch this video. We're going to now start talking about sound and hearing. Now, sound can travel in gases such as air, liquids such as water, and solid materials. We did learn with the video, though, that it doesn't travel in a vacuum. The simplest sound waves are sine waves, and they have a definite frequency, an amplitude, and a wavelength, and we've talked about those in the other videos. The human ear is sensitive to waves in the frequency range from 20 hertz to 20,000 hertz, or 20 hertz to 20 kilohertz. But we use the term sound for similar waves with frequencies above that, and those are called ultrasound, above human hearing, and below infrasonic, below the range of human hearing. Your dog can hear things in different ranges than you can. Sound waves may also be described in terms of variations of pressure at various points. In a sine wave, in a sine sound wave in the air, the pressure fluctuates above and below the pressure that's there in the atmosphere, P sub A. And the sine variation is having the same frequency as the motion of the air particles. The maximum variation in pressure above and below the atmospheric pressure is called the pressure amplitude, and that's called P max. Microphones and similar devices sense pressure variations, not displacements. Measurements of sound waves show that in the lowest sounds the human ear can tolerate without pain, the maximum pressure variation is on the order of 30 pascals. And a pascal is going to be a unit of pressure. It's going to be newtons per square meter. We'll say more about that later. And below. This is what the pressure is at sea level of the atmospheric pressure is 1.013 times 10 to the 5th pascals at sea level. If the frequency is 1,000 hertz, the corresponding amplitude, maximum displacement is about, amplitude is equal to 0.012 millimeters. That's really a tiny amount of displacement. Thus, the displacement amplitude of even the loudest sound is extremely small. The maximum pressure variation in the faintest audible sound of a frequency of 1,000 hertz is only about 3 times 10 to the minus 5 pascal. The corresponding displacement amplitude is about 10 to the minus 11 meters. This is extremely small. For comparisons, the wavelength of yellow light is only 10 to the minus 7, and the diameter of a molecule is 10 to the minus 10. You see, the ear is a very sensitive organ, and here's how it works. So this is the structure of the human ear. So when a sound wave enters the canal here, it causes the eardrum to vibrate. The vibration is transmitted to 3 small bones, and here's the names of the bones. This motion is then, in turn, transmitted to a fluid in the inner ear. The motion of this fluid is then impacted in a specialized hair follicles. These are very, very small hair follicles which sense the vibration, and the resulting nerve impulses are transmitted to the brain. This is a very sophisticated device. Like all other waves, sound waves transfer energy from one region to another. We talked about waves are transferring energy, not particles. We define the intensity of a wave, and this is the first time we've talked about intensity of a wave, denoted by I, as the time averaged rate at which energy is transported by the wave per unit area across the surface perpendicular to the direction of propagation. You really want to think about that definition for a while, because if it's coming at an angle, you've got to compensate for the angle. That is, the intensity I is the average power, and we talked about power already. It's watts per unit area. So you see the intensity of the faintest sound wave can be heard by a person with normal hearing is about 10 to the minus 12 watts per square meter, or 10 to the minus 16 watts per square centimeter. And here we just changed square meters to square centimeters, and that would be a good thing for you to check to make sure that you can do that way. Now the average total power, energy per unit time, which is what a watt is, carried across the surface by a sound wave equals the product of the intensity, power per unit area at the surface, and the surface area. And that's just multiplying the definition. Intensity is this, and if you multiply that, that gives you the total power. The average total sound power emitted by a person speaking in an ordinary conversation is about 10 to the minus 5 watts. And a shout corresponds to 3 times 10 to the minus 2 watts. So if all the residents of New York were to talk at the same time, and that's a bunch of people in New York, the total sound would be about 100 watts, which is equivalent to the electric power requirement of a medium-sized light bulb. Wow. Yet, the power required to fill a larger auditorium with a loudspeaker is considerable. So you see, we're talking about something different here than what we've talked about before. The intensity at an individual point is proportional to the square of the amplitude of the sound wave, and also proportional to the frequency of the wave. So you see, we're getting to the square of the amplitude, and also, it's also going to be the square of the frequency as well. Let's do an example now. So this is an auditorium sound system. In this example, we use the definition of intensity to calculate the power emitted by an array of speakers. So a sound system for a 2,000 seat auditorium is designed to produce a 1 watt per square meter sound intensity over the surface of a hemisphere, and a hemisphere is half of a sphere, 20 meters in radius. What acoustic power is needed from an array of speakers at the center of the sphere? Okay, so we have to think about this. So here's the setup. The total power needed is the intensity, power per unit area, times the area of the hemisphere. The area of a hemisphere is, now this is the surface area of a whole sphere, 4 pi r squared, where r is the radius of the sphere. But this is a hemisphere, so this is half of that. So we multiply through, and we do the calculation. And again, the hemisphere was 20 meters in length, so we get that this is about 2,500 square meters if we do this calculation. And we use some other, we use like 3.14 for pi. So the total acoustical power needed then is going to be the intensity, which was the sound intensity up here, times that area is going to be 2,500 watts, or 2.5 kilowatts. So that is how you could solve a problem like this. Now this is a very loud sound, and this is at the threshold of pain, and definitely in the range where permanent hearing damage is likely. And in fact, that's why many of your performers wear earplugs, and many people who go to concerts also should wear earplugs. Here's a practice problem if you wanted to practice something different with respect to that. So we've now defined what intensity is. Okay, we already talked about the power emitted by a sound source represents the energy per unit that is being carried away from the source by sound waves. If a sound wave has amplitude A and frequency F, then the power is proportional to the square of the amplitude and the square of the frequency. This is what I was talking about. So it's directly proportional. That's what that little fish-like symbol means. The power is proportional to the product of those two. So if the amplitude of a sound wave is doubled, then its power is quadrupled. Similarly, the frequency is increased. The power is carried by the wave will increase as the square of the frequency. The simplest source of sound is a point source. We assume that it all happens at a point that emits its power uniformly in all directions, like dropping the rock into the pond. We get the ripples. For such a source, the intensity at a distance r from the source is inversely proportional to r squared. You see, the intensity is going to be, this is the power of the sound source divided by the area at a distance of r, but this is 4 pi r squared, which is the surface area of the sphere. So you see it's going out in 3 dimensions, so it's going out spherically from there. The average intensity I2 through a sphere with a different radius then is given by a similar expression. And if no energy is absorbed between the two spheres, then the power must be the same for both. So we have multiplying all the way through, I1 is the same as I2, and so we get this expression, and that tells us that the intensity is inversely proportional to the radius. So the intensity at any distance r is inversely proportional to the square of the radius. That's what this means. This inverse square law holds for other various energy flow situations involving a point source, such as light being emitted. But we're studying sound in this course. Now we're going to do a just-in-time review of logarithms. So exponential logarithms are used for natural phenomena such as radioactive decay, where the rate of increase or decrease is proportional to the current value of the quantity. We also work with exponential growth and decay in the study of electrical circuits. So here is exponential growth. It grows very fast. So this is the graph of y is equal to, and we could say that this is e to the x because e is often used. Now we will encounter two types of logarithms, the common logarithm and the natural logarithm. The base 10 logarithm or common logarithm of a number y is the power to which 10 must be raised to obtain y. That is, y is equal to 10 to the log base y. And the log, the naked logarithm, is logarithm base 10. So for example, 1,000 is 10 cubed, so if I take the log of 1,000, I get 3. You can also use a calculator, and we'll demonstrate this. Linda will show you how to do the logarithms with the calculator. So we must raise 10 to the power 3 to obtain that. Most calculators have a key for this, and Linda will talk about that. Sometimes we're given the log of a number and asked to find the number. That is, if log base 10, here's the naked logarithm of y is equal to x, that means that y is equal to 10 to the x. So to solve for y, it's y is 10 raised to the power there, so y is equal to 10 to the x. There, in this case, y is called the anti-log of x, and again, you should be able to use calculators for this, and we'll talk a little bit about that in class with the calculators. Now, so this was the exponential function. This is the logarithm function, is a very slow growing function. That allows you to look at the comparison of logarithms on a graph without going to enormous numbers. Now another base that occurs frequently in physics is e. We talked about e, and this is called the natural logarithm, or ln, of a number y, and this is the power to which e must be raised to obtain y, and that means that y is equal to e to the x. That's the exponential function. These are inverses of each other. Another base that's used in computer science is things can be either 0 or 1. There are two states of nature there, on or off, and so logarithm base 2 is sometimes used as well. Now there are properties of logarithms with any choice of base, and here we're just saying it with base 10, but if I take the log of a product, AB, that's the sum of the logs, and the log of a quotient is the difference of the logs, and the log of a to the nth power is n times log of a. So you say, oh, these behave like exponents, and in fact, when you think about it, a logarithm is an exponent. Now, an important rule is that the log of 1, regardless of the base, is equal to 0, because 10 to the 0 is equal to 1. The natural logarithm of 1 is also equal to 0 because e to the 0 is equal to 1. And very importantly then, the log of 1 over a is the log of 1 minus log of a, but log of 1 is 0, so that is just minus log of a. Now sometimes we will be solving logarithmic equations, and so here's what we're going to solve this equation. 1/2 is equal to e to the minus alpha t, and we want to solve for t in terms of alpha. Well, you see, the capital T is in the exponent, so I'm going to take the logarithm base e, the natural logarithm of both sides. So when I take the natural logarithm of 1/2, I get ln of 1/2. And when I take the natural logarithm of this other side, since these are inverse functions, I get minus alpha t. So that means that t is equal to the natural logarithm divided by alpha. We will be solving logarithmic equations, and we'll talk more about that tonight in the VC. Now, since the ear is sensitive over such a broad range of intensities, it makes sense for us to use the logarithm intensity scale to be used. And the intensity level, or sound level, beta of a sound wave is defined by beta is equal to, and the units of this are called decibels. So beta is equal to, this is 10, and that is really a unit, dB, but then we're taking the logarithm base 10 of I, and we take it relative to I0. So in this equation, I0 is a reference intensity chosen to be 10 to the minus 12 watts per square meter. That, by the way, in this table is the threshold of hearing, and you see that is 10 to the minus 12 watts per square meter. The log denotes the logarithm base 10, not the natural logarithm ln. And the units of beta are decibels, abbreviated dB. A sound wave with an intensity I equal to I0 has an intensity level of 0 dB. So you see that's how we get it here, because that's going to be the logarithm of 1. The logarithm of 1 is 0, so that is 0 dB. This level corresponds to the faintest sound that can be heard by a person with normal hearing. The intensity of pain threshold, which is way up here, is 120 dB, and that's about 1 watt per square meter. There's 1. And corresponds to an intensity level of 120 dB. So here are some noise levels for various sources. And again, these are relative to this decibel rating. So let's test our understanding of this. So you measure a sound intensity, beta 1, 40 dB at a distance 5 from a sound source. You move further from the source and measure the sound intensity again. And this time you get beta 2 is 20 dB. What is your final distance from the source? And assume that the source emits uniformly in all directions, and it's a multiple choice thing. I'm not going to ask you multiple choice questions, but your certification exams often do. Okay, so we begin by noting that the sound intensity decreases by a factor of 10 for each 10 dB reduction in the sound intensity. Therefore, the sound intensity at a position 2 is 100 times smaller than it is at position 1. Now, we use the fact that the sound intensity itself varies as 1 over r squared. Putting these two together, we conclude that in order for the intensity to decrease by a factor of 100, position 2 must be 10 times further from the source than position 1. The correct answer is C. And just a little bit of a talking then about the strategy that you use to solve problems involving sound intensity. Quite a few quantities get involved in characterizing the amplitude and intensity of a sound wave, so it's easy to get lost in the maze of relationships. So it helps to put them into category. The amplitude is described by capital A or P max. The frequency, F, is related to the wavelength and the wave speed, as we've talked about, which in turn is determined by the properties of the medium that you're going through. Take a hard look at the problem at hand, identify which of these quantities are given and which you have to find, and then start looking for relationships that take you where you want to go. Also, you want to be careful when using the equation for the sound intensity level, because I and I0 must be in the same units. It's usually watts per square meter, but if they aren't, convert it to that unit. So here's another example. We're going to use the intensity equation to convert sound level to sound intensity. So a 10-minute exposure to 120 dB typically shifts your threshold of hearing temporarily from 0 dB up to 28 dB. Studies have shown on average 10 years of exposure to 92 dB sound causes a permanent shift up to 28 dB. What intensities correspond to 28 dB and 92 dB? Okay, so here's what we're going to do. We rearrange the equation, and we're dividing both sides by 10 dB, and then we take inverse logarithms of both sides. So we get I is equal to I0, and this is going to be 10, and the exponent here is beta divided by 10 dB. So if we put 28 in for beta, the dBs will cancel as units, and what we will get is the intensity, and you should do this calculation, but I0 is this, and then I put 28 in there for there, do the arithmetic, and so I get this is 10 to the 2.8 is the calculation we have to do, and so we take this times this, and we get that this is 6.3 times 10 to the minus 10 watts per square meter. So that is the intensity. When beta is 92, we're putting 92 in here for beta in the equation that we solved, and then we do the calculation, and we get 6.3 times 10 to the minus 3 watts per square meter. Now, and you want to be careful because remember that we were entering 1 times 10 to the minus 12, not 10 times 10 to the minus 12. Let's look at a different problem. Now we have a point source, and here's a bird that's making some noise, so that's the point source is right there. And we're having a guy that stands at a point P1 and a point P2. So consider a model of the sound emitted by a singing bird. There's the bird. And assume the bird is a point source of sound with constant power. So the intensity is given then by the equations for the, it's going to be beta is equal to 10 dB, the logarithm base 10 of I over I0. Now you're at point 1 and point 2. Now point 2 is further away. By how many dB does the sound intensity drop when you move to a point twice as far? So this is a distance from the bird, and this is twice the distance from the bird. So here's the way we set up and solve it. We label 2 points, 1 and 2, and we use the equation about beta twice. So beta 2, which is the intensity here, minus beta 1 is going to be, and we can factor this out, this is going to be 10 dB, this is logarithm base 10, that is I2 over I0, minus the logarithm of I1 over I0. But the difference of the logarithms is the logarithm of the quotient, and if I make the quotient, I have the log of I2 over I0 divided by I1 over I0, and so the I0s cancel, and I get that that is going to be log of I2 minus log of I0, and this is going to be minus, because it's a fraction again, log of I1 minus log of I0, so we get this is 10, and that's the ratio of the logarithms. So what we have is the difference in the levels is 10 dB times, but now you see I1 over I2 is the same thing as R1 squared over R2 squared, and so what's going to happen is this is the same, I'm just substituting I2 over I1 with R1 squared over R2 squared. So you see the distance R2 is twice the distance of R1, so I get R1 squared over 2R1 squared. Now the R2 squareds will cancel, and so that's going to be 10 dB times, and when you square the 2 you get 4, and so that's the logarithm of 1/4. So you see when I multiply this, plug this into a calculator, I get this is log of, that's the log of 1/2, and that's going to end up being a negative number, so this is going to be minus 6 dB. So a decrease in intensity by a factor of 4 corresponds to a 6 dB decrease in the sound intensity. Now, the decibel scale is logarithmic, so a factor of 2 in intensity corresponds to a 3 dB difference, and a factor of 8 corresponds to a 9 dB difference, and so on. Now, if 2 birds were singing, you'd multiply the power by 2. Here's a practice problem, and again, I will ask you problems like this along the way. And this often, not the proof, but often a question on certification exams, if you increase the intensity by a factor of 2, it's about a 3 dB increase. And if you decrease by a factor of 2, it's going to be a minus 3 dB sound level, or a 3 dB decrease. And here's a low-stakes assessment allowing you to practice this a little bit, eavesdropping. You're trying to overhear a juicy conversation, but from your distance of 15 meters, it sounds like only an average whisper of 20 dB. So you decide to move closer to give the conversation a sound level of 60 dB instead. How close should you come? This is a good problem, and one I often ask on finals. Not exactly that problem, but I ask you to be able to do a problem like that. In closing, then, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.